which I believe
Thank you.
is 76 Rutgers.
Yep.
Thank you.
Hello.
Hello.
Okay, team, do you have everybody here that you need?
Yes, yes, we do.
Okay. Let's see. Ed, why don't you start us off here, if you would?
Sure. I was interested in your flyaway rails, but I'd like to know how much drag reduction are you anticipating having by using them versus a standard lugs or on your rocket?
I'll let, well, we don't have a specific number that we aimed to reach with the drag reduction. We approach the problem more so as, hey, once this leaves the rail, there are these two protruding points off center that are with the rocket for the entirety of the flight. And we had seen some commercial flyaway rail guides, but maximum was for 4 inches and they were quite expensive. So we developed our own flyaway rail guides about 2.5 years ago, first used in the beginning of 2019. No, was it 20? It was 2018 actually. We did, no, 2019. Excuse me. So since then we've had only successes with them, and we've had no use of launch lugs or anything external in that regard. So that was kind of our approach.
Okay, because I mean, you stated in your presentation that you were using the rails for drag reduction, and now I'm hearing I'm not saying that you shouldn't use them, but if you're going to say you have drag reduction for use, then where's the numbers?
Okay, understood. Yeah, the main component was finding a hard attachment point for those lugs proved to be more and more difficult as we tried to go ahead, and seemed to be more of a problem rather than something working in our favor. So the initial aspect of it was, how do we make it a lot easier to build rockets of different sizes with hard attachment points? And the drag reduction was more so of a positive byproduct.
Okay.
Okay. Just to follow up on that, what's your what was your I don't have it in front of me, but what was your simulated altitude that you're going to reach?
Right. Ariane, if you could share the screen, we do have some media here, but it was a 27,300.
Yeah, just okay. Okay, so you're underneath your altitude, so reducing drag makes sense. You don't know how many times I've seen teams that are overshooting out, they've got their rocket overshooting and then somebody else is beavering away at trying to reduce the drag.
Yeah.
So okay, yeah. But I mean that, ease of building, that's a good reason, I think. Yeah. So Joe, do you got a question there?
Let me pass it on to Ed for a second. I'm looking something up before I want to ask.
Okay. What's the payload?
I'll let Aaron here take over. He's our telemetry payload lead. I can't hear you, Aaron. I see you talking, but he'll be quick with it. He's our best on the team with this. Zach, your name is incorrect in Zoom. You might want to change that out.
Okay, well, while he's starting his technical issue here, let me just ask a different question that we can talk about briefly and then come back to that. You had a great discussion on your additive manufacturing of your components. Really like that, good, filament choices. The one thing I didn't see is what filament did you use in your avionics bay?
I'll let Zach answer that one real quick.
And so a lot of the components like the sleds for the avionics were just PLA. like the support structure was steel rods. So in cases where we didn't think that there was any load bearing components, we just used the simplest and easiest material to print with, which was PLA.
Sure. And what infill did you use? Did you just print it 100% solid?
We have done that in the past, but we've, a lot of the components are so thin walled that it doesn't make much of a difference. We typically just leave it at 20 to 30% infill density.
Okay. Well, just tell you experience I had on the recovery team the year before last. We had the team open up their electronics bay, and their PLA payload sled just came out in little tiny pieces, which obviously caused a failure, and they had printed the thing at 10% infill. So it just simply wasn't strong enough.
Was it very thin as well?
And I think Joe, yeah, and so I think Joe could back me up that PETG is probably a little bit better choice for that, even though it's a little bit harder to print.
Yeah.
But that was a curiosity.
Well, actually, my comment.
Aaron, go ahead.
Hello, can you hear me?
Yes, that works as well.
All right.
What was your question, Joe?
Go ahead. Yeah.
Well, I was going to follow up a little bit on the infill in particular. Is what I found works best for me is almost no infill, like 10%, just
Really?
enough to get a good top surface, and then real thick walls and lots of top and bottom layers.
Yeah,
having all the strength in that. Although, yeah, a question I was refreshing my memory on before I wanted to ask is, of course, you used a lot of additive manufacturing, and you've got a lot of internal structure. There's lots and lots of threaded rods and lots of bolts and nuts. In the end, do you end up saving any weight this way? It's sort of one of the reasons for like PLA is it's a lot lighter than fiberglass. Well,
so
that was steel.
yeah, I mean, a lot of the reasons, like similarly for the flyway rail guides, for our design choices, for how we build the rocket, mainly comes down to manufacturability. So if it makes it easier to make, like more reproducible, and like we'll sacrifice a little bit of, like if it's not necessarily producing the weight, if it makes it easier to put together, then that's a trade-off which we'll typically.
Through our additive manufacturing, our interstage is entirely additively manufactured,
Right.
And we counted that only has definitely less than 30% infill, but what it does have is a thick radial wall that it does taper near the ears. However, we have added a little bit of extra thickness. Like if that was made out of aluminum, we probably could have gotten away with something a little different. But the interstage itself, we're able to manufacture it in about 16 hours while sleeping, and then and then able to input it into our rocket. And this specific interstage was flown 4 times successfully, and all times out of PLA without the steel support. It was only now with this one that our methodology is set a foundation that works, and then if we want to move forward, we can upgrade off of something that already has been proven. So we proposed for this rocket, it was going to be out of onyx with the steel supported rods to offer post tensioning. However, we've seen in an experimental flight to 15,000 under supersonic 2-stage with PLA without those steel support rods success.
Okay. Fair enough. Okay. So I think we got our technical problem solved. So Ed, why don't you re-ask your question there?
Yeah, what's the payload? Talk to me about it, because I didn't see anything in the presentation that talked about the payload.
That's mostly because we consider the payload to be our SRAD telemetry suite. So it's completely housed in the nose cone, and essentially it's a set of sensors and like a GPS, a transceiver, and like a Raspberry Pi for recording video. And so we kind of put those all together into the nose cone volume, And we use it mostly for redundancy with some of the COT systems, and also to record the data from the flight in a way that we can understand and easily interpret.
Okay. That doesn't, typically when I hear the word payload, there's some sort of experiment or some other purpose than just tracking the rocket going up and coming back down with telemetry information.
Mm-hmm.
So,
we told the line between the somewhat inert payload 8.8 mass, and what we do is we fill up, we use as much mass as we need to get our telemetry system in there, and then we have inert mass added. It's not necessarily an experiment as you may be used to. However, our entire team is dedicated towards expanding our capabilities upwards of 100,000 feet. So the SRAD telemetry system is important to us in that regard, that it's very important we test it as a completely separate system where the rocket will work without it. However, we have proposed that as our payload for this year's Spaceport.
Yeah, and on moving forward, that SRAD telemetry system is going to be the basis. We hope for the control system for an RCS system, controlled surfaces. And so this is just, it continues to help develop all the PCBs and the electronics that we have there, which will eventually become the brains for a reaction control system at the right beneath the nose cone. So that's what we're testing.
okay, so I had one other question. During the presentation, I saw lots of pictures of 3D drawings and completed products, but I didn't see any pictures of construction, something being made. So other than the parachutes, so are most of the components of your rocket presently built prior to this? I mean, is it like a 2019 or 2018?
No. So I can answer part of that. We had built a 6-inch to 4-inch rocket for November. We called it Eagle 2 version 4. What that offered us was the basis for our booster avionics, and the sustainer avionics. That AV bay has been continuously iterated since 2019. Now we have 2 of them. So we always have some on hand. Our kind of mentality, well, when we first started out, Spaceport 2018, we were building everything ready to make like days before it. And we've transitioned to, let's make sure we always have an AV bay that in 3 hours of work with the recovery team can be up and ready for a launch. So our AV bays had the superstructure. The sustainer was practically finished. The booster avionics bay did need quite a few revisions. And we had to redo all the body tubes and this and that. However, the drogue bay for the 4-inch is still the same drogue bay we used at Spaceport 2018 with the original paint. So I guess that one was already there. But the fins we manufacture per rocket, the fin can brackets, since our first usage in 2019, this is the same 4 fin can brackets. They've never broken. And the boat tails get reprinted pretty much for each launch. They're not load bearing, but they do get some heat distortion. And sometimes they get a little chipped up at the bottom after landing. So for about $10 and a good night's rest, we put another boat tail in there. Yeah.
Okay, so the design of the rocket body primarily has not changed for several years. You're just replicating what you've got.
It's so our goal is taking a 2-stage to 50,000 feet by the end of this year. And we've been progressing on that, not knowing where Spaceport would be for the last year. So this design started out in November 2020. Just a few months ago is when we had the 6 to 4-inch. And we take that design and we plan to build on it. But the idea for it came in about November 2020 under the line of thinking of taking ourselves past 30,000.
We're trying to keep as iterative design process. So we don't want to keep things by legacy, but like we try to build off of what systems we've already have. So like improving the avionics systems just a little bit, improving the telemetry just a little bit, and just replacing components as they get.
The goal is when we do launch it to 50,000, we build it. everyone on the team feels familiar with it because there are things that they understand that we've done in the past because they've worked and things have been iterated. But it used to feel for us that every rocket we built was completely different, new design, everything, and it was ending up being quite hectic and didn't always prove itself to work out well.
Okay, very,
Uh,
very good. A lot to be said for an iterative approach for something like this. Okay, our time is up. Thank you very much to all of you for a good presentation and a good talk. And you all are released, and we'll turn to our next team.
All right, thank you very much. Good luck.
Thank
and
you.
Okay.